Okay. So I told you there are some basic signals. Okay, basic signals. There are some things called basic signals, and I told you that there are uh, uh, 5 or 6 basic signals mostly we use. Okay, so one is unit impulse signal. Unit impulse signal. Uh, in discrete time, we represent it, in continuous time, we represent it as delta t, and discrete time, we represent as delta n. Okay, and one other one is unit step signal. Okay, so normally ut, un. Another one is sinusoidal signal. Sinusoidal signal normally represent like this mathematically. Okay, this amplitude, this is a frequency, and this is a phase. Okay, and other one is complex exponential signal. Exponential signal that is mm, uh, somewhat like this. Okay, e to the power j omega t. This is plus or minus. This omega also you can write as 2 pi f. Okay, 2 ft. Okay, and and I told you that if you consider sinusoidal signal or complex exponential signal, there is one frequency component. Okay, so that's the frequency component. This one is the frequency component. Okay, so both have one frequency component. Okay, component. And if there is a one frequency component, it will be a sinusoidal signal. Actually, this complex exponential signal is not a practical signal. This is a mathematical signal. You can understand that because using Euler formula, we can write this as a cos omega t plus j sine omega t like this. Okay. Okay, cos omega t plus j sine omega t. Using Euler formula, you can write the complex term, this e j omega t like this. You know that it is e j theta is equal to cos theta plus j sine theta. This is the Euler formula. Okay, Euler formula. Okay, so you can see that this part is imaginary part. This part is imaginary part. Okay, imaginary part. So practically we can't generate this signal. This is a mathematical signal. Okay, so we consider this also has a one frequency component. This is also considered as a periodic signal, and it has a one frequency component. Okay, okay, this is the frequency component. Okay, so sinusoidal signal is a practical signal, and definitely it has a one frequency component. Okay, and this is one frequency component also referred as harmonics. Okay, harmonics. Okay, so if we consider any arbitrary signal, okay, any arbitrary signal, it can be a sawtooth signal, square wave signal, okay, square wave signal. These uh, these can be mathematically represented as a collection of harmonics, okay, as a collection of sinusoidal terms or complex exponential terms, okay. So uh, actually that is practically happen. Okay, we can see it if you consider. Okay, if you have to signal generate, I told you that. Okay, if you combine both signal, okay, and if this one has frequency and this has the same frequency, you will have a sinusoidal signal here, and the frequency are changing, you have uh, repetitive signal, but it is not the sinusoidal signal. Okay, and uh, if you combine around 8 9 signal, so you can generate approximately a sawtooth signal or triangular signal. Actually, triangular signal you can generate. Okay, likewise this is practically happening. Okay, okay, so this is the Fourier transform. This is the theory behind the Fourier transform. We are going to represent the frequency component or frequency domain of a signal. Okay, so that is the uh, Fourier transform we have already told. Okay. Mm. So Fourier analysis. Okay, sorry, Fourier analysis. Okay. So basically Fourier analysis has two types. I think this one also discussed we have. Okay. One thing is Fourier series representation. Other one is Fourier transform. Okay. Fourier series representation we normally use for periodic signal. Periodic signal. This is for non-periodic signal. Okay. This is for non-periodic signal. And Fourier transform has two forms. Okay. One is complex exponential Fourier series representation. So there we can represent any periodic signal, actually not any periodic signals. Okay, the signals only satisfy the Dirichlet condition. Okay, there is some condition called Dirichlet. Okay, if a signal is satisfy this Dirichlet condition, we can represent that signal as a collection of complex exponential term. Okay, any signal xt can be represented as a collection of complex exponential signal. Okay, like this. Okay, okay, as a collection of exponential signal. So this k can be minus infinity plus infinity. Okay, this k can be minus infinity plus infinity. So we have weightage, we have coefficients. This coefficients is said to be Fourier series coefficients. Okay, Fourier series coefficients, and because this is a complex exponential Fourier series representation, this is referred as complex exponential Fourier series coefficients. Okay, complex exponential uh, Fourier series coefficients, this ck. Okay, this ck can be calculated using the integration. Okay, the given signal should be multiplied by e to the power minus jk omega t, omega naught t. Then you need to integrate it within one period. Okay, and you should divide it by 1 over t naught. Okay, so in this way you can calculate the Fourier series representation. Okay. Okay, so this xt, this is for continuous time. This is for continuous time. Okay, so the Fourier analysis we used both continuous time and discrete time. Okay, so if you have any continuous time or discrete time periodic signal, you can represent it as a Fourier series representation. Okay, as a collection of complex exponential signals. Okay, so that is called as complex exponential Fourier series representation. And another one is there, that is a trigonometric Fourier series representation. There you can represent any signal. Okay, any signal as a sum of, okay, as a sum of uh, sinusoidal signal. Okay, as a sum of sinusoidal signal and cosine signal. Okay, so as a sign of sinusoidal signal, actually DC component is there. Okay, so a k cos omega naught kt plus bk sine omega naught kt. Okay, so you can see that now xt can be represented as a collection of sinusoidal signal. Okay, so the DC component also will be there. Okay, DC component also will be there. Actually, that is this omega naught is uh, equal to 0. Okay, so actually we are mainly focusing on this complex exponential Fourier series representation. Okay, so the questions come to your exams will be complex exponential Fourier series representation. Okay, so you no need to much pay your attention to trigonometric Fourier series representation, but you can see it. Okay, okay, and in the same manner, these are trigonometric Fourier series coefficients ak and bk. So you can evaluate ak and bk. There is an integration. Okay, using that integration, you can evaluate. Okay, as I can remember, it is xt. This should be multiplied by sine signal sine omega naught kt, and this one should be multiplied by cos omega naught kt. I'm not sure this. Okay, maybe wrong. Okay, but it is look like this, okay? And the period, this integration should be within a period, as I can remember, okay? But we are not much going to this part. We are mainly focusing on this complex exponential Fourier series representation, okay? Okay, and also Fourier transform. Fourier transform we use for non-periodic signal, okay, non-periodic signal. Actually, in Fourier transform, we directly convert time domain signal into frequency domain signal. Here, actually, we are find the frequency component. That is also some kind of conversion, time domain to frequency domain. Okay, but here we have a time domain signal, a collection of time domain signal. But here, the signal will be directly in frequency domain. Okay, so we will see it. We will do some questions, then you can have idea. Okay, okay. And another thing is, actually this is for the continuous time non-periodic periodic signal, continuous time periodic signal. There you have to do the integration. Okay, but for the discrete time signal, the same theory is there. Okay, so any discrete time signal normally we represent as xn. This n is the sample number, you already know that. Okay, xn as a collection of uh, uh, complex exponential term. Okay, but this time this addition is not minus infinity to plus infinity. The addition will be k from 0 to n naught minus 1. Okay, this n naught is the period. Actually, this omega naught is also omega naught is referred as a fundamental frequency. Okay, fundamental frequency. So that is 2 pi by t naught. This is the period. Okay, so this is the period. Okay, so here the n naught is the period of discrete time signal. Okay, discrete time signal. Okay, so in the same manner you can calculate this as ck e to the power jk omega naught n. Okay, omega naught n. Okay, sometimes this omega uh, represent in capital form also. Okay, so that is uh, the symbol we use, but the theory is same. Okay, and this omega naught is equal to 2 pi divided by n naught. This n naught is the fundamental period of the signal. Okay, so in continuous time signal we know that period. Okay, how to find the period? Maybe you can simply remember that. Okay, if this is a continuous time, if this is a repeating signal, okay, we select two consecutive repeating point, and calculate the time difference between this point and this immediate repeating point. Okay, so that is the period, that is the fundamental period for a continuous time. In the same manner, for discrete time, we have samples here. Okay, we consider consecutive repeating sample and calculate the number of sample 1 2 3 like this. Okay, so that the number of samples also related with time. Maybe you know that the time is nps. Okay, so n always uh, related with time. Okay, so this 2 5 n naught, so this is the sample number of sample actually. Okay, we will see it. Okay, discrete time. Okay, and in the same manner you can calculate the ck, but this time ck is not for to find the ck you no need to do the integration, because you know that. Okay, for a continuous time signal, if you want to add all these points, what you need to do, there are infinite points, no, infinite time points. Okay, so you can't add them all. Okay, you need to do the integration. But if you consider this discrete time signal like this, okay, there are finite values, so we can add this value 1 2 3 likewise. Okay? So here the there is no need of an integration for the discrete time signal, so you can have a summation. Okay, summation. The summation also will be from n from 0 to n naught minus 1. Okay, and xn e to the power minus jk omega naught n. Okay, so in this way, so this is actually the Fourier series representation of discrete time signal. Okay, Fourier representation of discrete time signal. And in DSP, we are mainly focusing on this discrete time Fourier series representation. Okay, not the continuous time Fourier series representation. Okay, so your exam questions will come from these two equations, Fourier series representation question. Okay, these two equation. Okay, so we will try to understand this equation. Okay, so we will do one example actually. Okay, uh, so this is your reference book. I will select exam, so you can see that uh, frequency frequency analysis of a signal. Okay, so this is so in Fourier transform, Fourier analysis, actually we are going to do a frequency domain analysis, frequency analysis of a signal. Okay, so you can see if you need you can see this introduction. Okay, so that is a mathematical tool. Okay, okay, so you can see that uh, this useful in analyzing and designing linear time invariant system. What it mean actually? Okay, so sometime, for example, if you consider a filter to design a filter, the filter, you know that. Okay, you know a filter. Okay, normally if you consider a filter, if you apply some frequency component, okay, frequency range, okay, so you can get the desired frequency range. That is the idea of a filter. Okay, so here you give some frequency range and you have output frequency range, desired frequency range. Okay, so you can see that this filter, the analyzing the filter is the time domain analysis is not much important, but frequency domain analysis is much more important for filter because it is related with frequency. Okay, so analyzing a filter normally done in frequency domain, and also if you need to design this filter, definitely you need to have the frequency domain response. Okay, frequency domain response. Okay, so I think you have learned about LTI system. Have you learned about LTI system? We will learn. I will tell this uh, after. Okay, so LTI system means linear time invariant system. Okay, so there is some properties related with system, linear, non-linear systems, time variant, time invariant system, causal system, non-causal system, like this. Okay, so I will tell this later. Linear time invariant, what is the meaning of linear time invariant? But if you consider a linear time invariant system, okay, and if you give an input to this system, you have an output. Okay, and if you give a uh, impulse to this system, you have output. Okay, let's say that output is ht. Okay, this ht is referred as impulse response. This ht is referred as impulse response. Okay, actually we can characterize this LTI system using this impulse response ht. Okay, ht means the impulse response. That means if we give an impulse to the system, output is the ht, impulse response. Okay, so we normally use ht to characterize this system. Okay, so normally there is a output input relationship on LTI system. The output signal is equal to input signal convol impulse response. Okay, like this. Okay, and if you consider a filter, this ht is not much interesting. Okay, we need this ht in frequency. Okay, so you need to convert this ht into frequency domain. Let's say that that is h omega. This is normally referred as frequency transfer function. This is impulse response. This is normally referred as frequency transfer function. Transfer function. Okay, transfer function. Okay, and this xt Also, you can convert into frequency domain x omega, and this one also you can convert to frequency domain y omega. Okay, actually, if you convert, this convolution will be disappeared. Okay, and this will be a simple multiplication. Okay, we will discuss them later. There are some properties related with Fourier analysis. Okay, so using that property, we can we have we can get rid of this convolution uh, by converting the domain of a signal. Okay, by transforming the domain of a signal. Okay, so so this h omega. Okay, actually, when we are doing a filter design, definitely we need this frequency transfer function. Okay, based on this frequency transfer function, we calculate the order of the filter and also the stop frequency, then cutoff frequency, pass band. Those are normally defined in this h omega. Okay, okay. So that is important. This frequency domain analysis, actually that details is here. Okay. So actually it is like this. Okay. So if you have a direct light, that means it is white. It is white light. So you know that that white light is uh, the white light has several color. Okay, several color. So this each color represent one specific frequency. You know, specific frequency. So these frequency are harmonics. We can consider as harmonics. So by uh, by uh, by by adding these harmonics, we can create a white light. Okay, the same thing is there. So if there is a signal applying Fourier series representation, we can find these harmonics of that signal. The harmonics which is constructed this input signal. Okay, so that is the Fourier series idea. Okay. Okay, so continuous time periodic signal. For the continuous time signal, this is the Fourier series representation. This 2 phi f naught, you can I have write as omega naught. Okay, this 2 phi f naught I have written as omega naught. Okay, so both are same. Okay. You see k. Okay, the k is an integer value that can be minus infinity to plus infinity. Okay, this k is an integer value, minus or plus integer value. Okay, don't forget that one. Okay. Okay, so here this is for the continuous time. Okay, this is for the continuous time. I think I have written the free equation correctly. Okay, so here it is plus, and here you can see it is minus. So this 2 5 f naught is omega naught. Okay. This omega naught is represented as 2 5 divided by t naught. T naught is uh, I'm sorry, okay. Okay, and we no need to apply, we no need to bother about continuous time signal. We can wait a minute, okay. Okay, we can focus on only discrete time signal, okay. uh, okay, so you can see that this is 2.1, that is the Fourier series for discrete time periodic signal, okay. So actually we are going to focus in this uh, in this section of okay, and you can see that uh, so don't worry, the same thing is here, okay. So you can see that 25 divided by n, 25 divided by n, that is what? 25 divided by n, what is that? Can anyone tell me what is the 25 divided by n? So I have written that equation in another way, jk omega naught n, but you can see that here it is somewhat different, 25kn divided by n, okay. So what is actually this 25 divided by n, what is that? 25 divided by n, what is? N is, that is the period actually, that is the period with period n, okay. So you can write this, okay. We are given a periodic sequence xn with period n. Period n means, okay, if you have any sample and again you will get the same sample at n plus n, simple n plus n. So this sample is equal to x n plus n sample, okay. So this is the condition for the periodic, okay. So now you need to understand these things. You should be able to understand, okay. And 25 divided by n, that is frequency, okay. So this one, 25 divided by, so I have written n naught, but you can, here in that one only n is there, okay. Actually I used to write the equation in this way, okay. Don't get confused, okay. So these are only related with symbol. We can use different symbols to represent anything, okay. Okay. Okay, so actually this equation you need mainly. I forgot one thing. The ck, when you are finding the ck, you need to divide it by that 1 over n naught, 1 over n naught. Here it should be 1 over n naught. You need to divide this by the period n naught, okay. So you can see it, okay. Okay. So we will try to do one uh, example, okay. Uh, uh, Actually, we can do this example, but I think we will do another one. Okay, this kind of signal, we will take this kind of signal, okay. I will take that kind of signal. I will take that kind of signal. Okay. Actually, just try to understand this one. This is not much difficult. This is very easy. Okay. Then you can do any calculation. Okay. So this is the n and this is xn. Okay. And let's say that we have a signal like this. This is 1, this is 2, 3, 4. And only we take 3. Okay. And again, sorry, this is 2, this is 1. No. Again, this is 2, this is 1. This is 2, this is 1. This is 2, this is 1. Again, this is 2, this is 1. This is 2, this is 1. Okay. Okay. So this is a discrete time signal. This is a discrete time signal. Okay. And this is go up to plus infinity, and here it is coming from minus infinity. Okay. The same. So this is the signal. Okay. Okay. First tell me, is this periodic or not? Quickly tell me, this is periodic or not? Quickly tell me, don't get much time. Okay. We don't have much time. Yes, that is periodic. Okay, thank you. This is periodic. This is periodic. Ah. Then if it is periodic, can you tell me what is the period? Just tell me what is the period. Quickly tell me what is the period of this signal. Yes, that is correct. Okay, what about others? I think I have told how to find the period of discrete time signal when we are doing the sampling. Okay. So how to find the period? You need to select some sample. Okay. Let's say that I am selecting this one. Okay. Then we have this one. Okay. This one. Okay. And you need to see where this is repeating again. Okay. So you can see that this one is repeating here. Okay. This one is repeating here. So you need to calculate the number of samples from here to here. So the number of sample will be 1, 2, 3. Okay. And if you consider this one is repeating here. You can calculate the number of sample from here to here. That is 1, 2, 3. Okay. So the period N naught is 3. Okay. So omega naught is 25 divided by 3. Okay. So we have found the period, and now we can we can try to represent this as a collection of complex exponential signal. So xn we can represent as a collection of complex exponential signal ck e to the power jk omega naught n. Okay, so we know the omega naught, that is 25 divided by 3. Okay, so you can, if you need, you can apply this omega naught value to this one. Okay, or maybe if you have written here it, and you can keep this as it. Okay, anyway. Okay, so this so you can see that the period is 3. Okay, so you need to you need to do, you need to do this addition from 0 to k, from 0 to n naught minus 1, that is up to 2. N naught is 3, n naught minus 1 means 2. Okay, so 0 to 2 you need to find this addition. Okay, you need to find this addition. Okay, so that is very simple. Okay, so you can see that if we have expand this. Okay, expand this, we can write this as, if k is 0, so you have c0 e to the power jk, k is 0. Okay, so e to the power 0, it will be 1. Okay, it will be 1. So this e part will be, okay, okay. So this E you can remove. Okay, you can remove the E. Okay, so it will be only C naught plus, then K is 1. So that means C1 e to the power J, K is 1. This is J, okay, K is 1. Omega naught, that is 25 divided by 3 N plus, now K is 2. That means C2 e to the power j, k is 2, omega naught is 2 5 divided by 3 n. Okay, so this is the Fourier series representation, complex exponential Fourier series representation. Now you need to find these Fourier series coefficients. Okay, so you have to find 3 Fourier series coefficients. Okay, you have to find 3 Fourier series coefficients. That is, one is so to find the Fourier series of coefficients, you have this identity, that is Ck is equal to 1 over n naught multiplied xn e to the power j minus j omega naught k n. Okay, this is the identity, and this n from 0 to n naught minus 1 again. Okay, so that is the equation we have written, no? N from 0 to n naught minus 1. Okay, so you have to apply this equation, this identity. You can use this uh, identity to calculate these Fourier coefficients. Okay, so when k is 0, okay, the c naught will be 1 over n naught. N naught is 3. Okay, and n from 0 to 3 again, xn e to the power minus j omega naught is 2 5 by 3 kn. Okay, now you have to expand this with respect to n. Okay, so if you expand it, 1 over 3 is there. Okay, x0 e to the power minus j 2 5, k is 0 here. So e to the power will be 0, no? So all the terms e to the power will be 0 because this k is 0. Okay, so it will be 1. So x naught e naught, that means it will be 1. It will be 1 plus x1. That means n is 1. Okay, n is 1. Uh, because 0 to 2. Okay, n naught minus 1. No? Okay, so you need to evaluate up to 2. N naught is 3. 3 minus 1, it is 2. Okay, and x1, again n is 1 here, but k is 0. Again these terms will be 0, so it will be 1 plus x2 e to the power k is 0 again, n is 2 but k is 0, so it will be 1. Okay, so this will be the c naught coefficient. And what is the c naught coefficient? X naught is this is x naught, that is 2, x1 is 1, x2 is 0. Okay, so this is 0, 1, 2. Okay, so this will be 0, this will be 1, this will be 2, this will be 1, this is 0. Okay, so x0 is 2, x1 is 1, x2 is 0. So it will be 1, c naught will be 1. In the same manner, when k is 1, you can find C1 coefficients, okay, this coefficients using the same identity, this one. So C1 will be 1 over 3, again 1 over n naught, the summation from 0 to 2 again, xn e to the power minus j omega naught kn. Okay, and you need to expand this again. So 1 over 3 is there. Okay, so x0, now k is 1, but again n is 0, so e to the power 0, it will be 1. So plus, now n is 1. Okay, so x1 is there. Now e terms is there. Okay, because k is 1, n is also 1. Okay, so it will be minus j omega naught is t5 by 3, k, that is 1, and n, that is again 1. Okay, so this terms is there, and again x2. Okay, x2. Okay, so e to the power minus j omega naught is 2 5 by 3, j k is 1, n is 2. Okay, so you have this term. Okay, so x naught is 2, x1 is 1, and this x2 is 0, so this term cancel. Okay, so c1, you can see that for the c1 you will have 1 over 3, 2 plus e to the power, this is 2, 453. Okay, minus j 453. Okay, so you can find this, you can use the Euler formula, you can expand this cos 453. So yeah, cos 453 plus j sine 453. Okay, so you can see that it is a complex number, x plus jy, like it is a complex number. Okay, so you can find the c1. Okay, okay, so can you try to find c2? Just try to find c2. I give you 1 minute or 10 minutes, maybe not 10 minutes, 5 minutes. Try to find c2. That means k is equal to 2. Okay, so try to find this one. Okay, and C2 I will try to do. Okay, so I think that is also very easy. So that will be 1 over 3. Okay, 1 over 3. Okay, the k is equal to 2 now. Okay, so again x0 will be e to the power 0. So x0 only is there, that is 2, plus x1, now n is 1, x1 that is 1, e to the power j omega naught k is 2, n is 1. Okay, so omega naught will be again 2, 5, 3. So it will be the same one, no? E to the power minus j 4, 5, 3. Okay, so I think the C1 and C2 are identical. Okay, okay. Now tell me, can you find this complex number C1? Can you find what is C1 and can you find what is C2? So you need to find this term cos 453, then sin 453. What is that value? Cos 453 and sin 453. Can anyone tell me? Okay, 0.99. And what is sin 453? What is sin 453? 0, 0, so on. No, okay. So you can see that we can write this C1 as 1 over 3, 1 over 3, 1 over 3, 2 plus 0.99 plus j 0.77. Okay. Then 2 plus 0.99. So you can write this as 299 plus j 0.77. This should be divided by 3 and this should be divided by 3. Okay, so you can find this C1 like this. Okay, and the C2 value also will be the same. Okay, so 3.99, it is approximately 3. So that will be 1 divided by j 0. We can put 2 here. divided by 3, 2 and 1 is there. So it will be 5 and 6, no? 2, 5, 6 around. Okay. So this will be the C1 and C2. C1 and C2. Okay. Okay. Now, so I think now very easily you have found these coefficients. Okay. So here you can, the C naught is 1. Sorry. Yes, C naught is 1. That is a real value. And C1 is 1 plus J 0, 2, 5, 6. And C2 is also 1 plus J 0, 2, 5, 6. Okay. So you can apply this value here. Okay. So that is the Fourier series representation. Okay. So we have found xn as a collection of complex exponential terms. Okay. So this terms, what is the frequency of this term? That is the frequency is omega naught is 0. Okay. So that frequency is 0. That means this is a DC component. This is referred as the DC component. This is the DC component of the signal. This is the DC component of the signal. And what is the frequency of this one? 253. So here the frequency is 253 and this frequency will be 453. Okay. So you can have, okay. And why you need to do this up to n naught minus 1? Because if you add another sample, that means this sample. Again, you need to find this one. You are calculating this one. Okay. So already you take this. Okay. So if you take n sample and not sample, you are repeating the same point. Okay. So whatever you need to add from one sample to other sample, that will be enough. Okay. So that is why we need to get this sum from 0 to n naught minus 1. From any sample to next repeating sample. Okay. So I hope you get it. Okay. Okay. So I think if you are given any any if maybe you can try to do this one also. Okay. So here what is the period of this one? Can anyone tell? If this signal is there, what is the period of this signal? Quickly tell me. So you can see that this is a 0 and this is the n sample. Okay. So this one is repeating here. You can see. Okay. Then you need to calculate from here to here. So it will be n naught 1, n1, n minus 1. So the frequency will be so the period will be n minus 1. No, 1, 2, 3, n. No, period will be n. Okay. So period will be n because 1, 2, because this is 1. No, this is 1. No? So 1, 2, 3, so period will be n. Okay, sorry, period will be n. Okay, so period will be n here. Then maybe just try to do this one. Okay, so this one also not much difficult. You can try to do this one by yourself. Okay, so try to prove this one. Okay, try to get this answer. If you have any problem, please ask me. I will try. I can help you. Okay, so maybe if you can do this, you can. If you have any problem, you can send me a WhatsApp message, then I can help you. Okay. So try to do this by yourself. I think it is not much difficult. Okay. And another thing is, okay, so you can see that there are some examples here. Okay. So try to do this example also. Okay. So solutions are there. So you can practice. Okay. Actually, same kind of question will come to your exam also. Okay. So try to do this example also. Okay. Uh, okay. So I think that is okay. Okay. Another thing we need to see. Okay. Another thing we need to see. Actually, we are not much discussing about this conversion of Fourier transform. Okay. But for the Z transform, we are find the conversion. Okay. Actually, conversion of the Fourier transform means Fourier analysis means some series goes to infinity, but some series not goes to infinity. It has a finite value. Okay. So if it has a finite value, it is referred as convergent series. Okay. So the simple idea is there. Okay. Another important aspect is there. Okay. Okay. Now you can see that these Fourier coefficients, okay, these Fourier coefficients are complex value. These Fourier coefficients are complex value. Okay. So the Fourier coefficients Ck can be a complex value. So it is look like xk plus JYK. Okay, so it is like this. Okay, and you know that we can represent this complex number in a complex form, a complex plane. Okay, this is referred as complex plane. X-axis is the real axis, y-axis is the imaginary axis. This is referred as complex plane. Okay, complex plane. Okay, so you can represent this CK complex number here. Okay, so SK will be the real value and yk will be the imaginary value. Okay, and imaginary value also can be 0. Okay, because this yk can be 0, so then it will be a real value. Okay. And if you consider this value, this is we called the magnitude of this complex number. Okay, so that is ck, magnitude of ck. Okay, so magnitude of ck you can find using Pythagoras theorem. Okay, so it will be xk square plus yk square root. That is the magnitude of this complex number. And this theta you can refer as the phase. Okay, you can refer as the phase. Okay, so this phase of ck can be find, actually you can use the tan inverse. Okay, so it will be tan inverse සම්මුඛ පාදයේ බෙදීම කරණය නේ, සම්මුඛ පාදයේ බෙදීම පද්ද පාදය yk divided by xk. Okay, so this is the magnitude of ck and this is the phase of ck. Okay, so phase of ck maybe you can written like theta. Okay, so again you can represent this complex number using this magnitude and phase. Okay, so this will be yk will be, okay, yk will be magnitude sine theta. Okay, so ck, magnitude of ck sine theta. Theta means actually phase of ck. Okay, okay, and xk again you can represent this one. So this, if this is r, xk will be r cos theta. So this is the magnitude of ck magnitude cos theta. Theta is the phase of ck, like this. Okay, so then you can write the same ck, the complex number, as magnitude of ck cos phase ck plus j magnitude of ck sine phase ck, like this. Okay, and what is this? Using Euler formula, you can write this ck as magnitude of ck e to the power j phase of ck. Okay, so in this way also you can represent represent this ck value. Okay, this is we call polar form. This is we call polar form. This is we call rectangular form. Rectangular form. Okay, so you can represent this ck in this direction, in this way, or in this way, or in this way. Okay, so you can see that if you consider a Fourier series coefficients, okay, there is a magnitude, that is ck magnitude, and there is a phase. Okay, okay, so sometime we plot, okay, we have ck value, here in our case we have ck, what is 1 is 0. Okay, sorry, c naught Okay, we have three values, C0, C1, C2. Okay, we have three C value, C0, C1, C2, Ck value. And what is the magnitude of C0 in our case? C0 is 1, no? C0 is 1. So it is a real value. Okay, so magnitude of 1 is again 1. Okay, so magnitude of C0 is 1. And what is the magnitude of C1? The magnitude of C1 you need to calculate. Okay, because it is 1 square plus 0.256 square. Okay, so magnitude of C1 will be 1 square plus 0.256 square root. This is the magnitude of C1. Okay, then you can find this value. You can put here. Okay, so it is maybe bigger than 1. Okay, so this is the magnitude of C1. In the same manner, you can find the magnitude of C2. Okay, so you can plot the Fourier coefficients. You can plot magnitude with respect to Fourier coefficients. This is the Fourier coefficients. This is the magnitude. Okay, so you plot magnitude versus Fourier coefficients. Fourier coefficients magnitude versus Fourier coefficients. This is referred as magnitude plot. Magnitude plot. Okay. In the same manner, there is a phase also. No? Okay. So in a phase, same way, you can plot phase with respect to Fourier coefficients. C1, C2 is there. And what is the phase of C0? Tell me what is the phase of C0? C0 is 1. C1 is 1 plus 2 pi 6 j. C2 is again 1 plus 0.256 j. Okay. So here the magnitude is 1. Here magnitude is 1 square, 256 square root. This one also same. And what is the phase of C0? Tell me what is the phase of C0? Quickly tell me. Don't get much time. What is the phase of C0? Complex plan එකේ කොතනද ඔය C0 කියන එක තියෙන්නේ? C0 කියන්නේ මෙතන. මෙතන තමයි 1 කියන එක තියෙන්නේ. මෙයාගේ phase එක කීයද එතකොට? මෙයාගේ magnitude එක මේ දිග. ඒ කියන්නේ 1. මෙයාගේ phase එක කීයද? මෙයා x axis එකත් හදන කෝණය කීයද? What is the angle he makes with x axis? Yes, that is 0. So it is a real number. So the phase will be 0. Okay, so this phase will be 0. And what is the phase of C1? For that one, you need to get tan inverse value of, this is the front leg 0.256, and this is the joint leg, that is 1. Okay, so you need to get the tan inverse, then you can get the radian value. So that is the phase of C1, and the same phase will be there for C2. So here you plot phase versus coefficient C2. The phase of the Fourier coefficients versus phase. This is we call as phase plot. Phase plot. Okay. So this magnitude plot and phase plot are somewhat important. Actually, in spectrum analyzer, we can see this magnitude plot as well as the phase plot. Okay. Okay. So this phase plot and magnitude plot are used to get the idea about the frequency component. Okay. Okay. So that is the things we need to learn actually. How to represent discrete time signal as a Fourier series representation, and also draw the phase plot and magnitude plot. Okay. So maybe you can get around more than 10 marks for the exam. Okay, more than 10 marks for the exam in this section. Okay, so I'm not going to do examples here. Okay, so try to do this example by yourself. I think it is not much difficult. Okay, you can easily do this. Okay, so try to do some examples by yourself. If you have any problems, you can ask me. Okay, so there are some examples, and I think I have uploaded the secondary books that Shom outline books. In Shom outlines book, there are many solved questions, solved problems. Okay, solved problems are there, so you can try those solved problems. Okay, so if you have any problem, you can ask me. Okay, actually related with this Fourier series. Okay, we have some what is called uh, properties. We have some properties. Actually, these are the properties. Okay. No, this is the properties of Fourier transform. Related with the Fourier series also, we have some properties, list of properties. Actually, properties means if you see some common thing, it is considered as a property. Okay. So these properties you can use to easily find Fourier series coefficients. Okay. So I am not going to discuss any properties here, but maybe some properties are here. Maybe you can try to find and try to see and try to apply one or two these properties also. Okay? So that is also much difficult. Okay. Okay. So I hope that will be okay for today. Okay. So in next week, we will do Fourier transform. Okay, we will see the Fourier transform. Today we see Fourier series representation of a periodic signal in discrete time signal. Okay, so that is what we are doing. And also we see the phase plot and magnitude plot. Okay, so I will stop here.